another episode of Rapid Turn, episode 9 I think. On this episode we're going to explore the power and the rigidity and the torque of Rapid Turn. We'll do a tough thread testing test in steel to find out what you can expect and what its limitations are. Cheers. Scary. Well, it's just a high-speed steel tool that I've knocked up because I don't have the right size tool holder. So it's just on the verge of chattering there. Right on the edge of it there. Didn't like the sound of that last pass. I'll inspect that a bit more closely. I've just carried on. It's right on the edge of whatever's going wrong, and I won't know unless I crash it, so let's just keep going. If it slows the motor down, that mucks up the pitch of the thread, which puts a bigger cut on, and then that mucks up the pitch of the thread again, which puts a bigger cut on, so you could get meltdown really fast. But the only way I'm going to know is to try it. So I'm getting alternatively large and small cuts here. I'm not sure why that is. Ooh, hear the motor slowing down? Now it's alright. So we're right on the limit here. Slowing down again. So it's probably correcting itself as it registers the motor slowing down. Yeah, see, it's picking up where it missed a bit of a thread there. So obviously you can't take big cuts with the drive system. Yeah, that's right on the limit there. And it's interesting, it wouldn't let me feed hold halfway through a pass. It took it to the end first. So, okay, if I go back to cycle start again, see what happens. I think the tool might be chipped. Sound of it, it's rubbing. Well, it almost did it. That's obviously the limit with that particular tool. Of course, it's only a high-speed steel tool. I'll just inspect it a bit more now and get back to you. Well, that was a really interesting test. Let's just look at the results. The tool was just a little rough high-speed steel tool I grabbed just to test it out. It hasn't actually chipped, although it's looking a little tired. The thread that we cut was a 35.82 diameter OD thread, 50 millimeters long, 2 millimeters pitch, and an ID of 33.38. So that's a 1.22 millimeter depth of thread in free cutting mild steel. So that's a fairly hefty sort of a task for Rapid Turn. Remember, they're only designed for light cuts. But I wanted to know, how far can you go? Where are the boundaries? You know, you don't know if you don't try. So this is a little bit too difficult for it, with that tool anyway, because what happens is that it slows the motor down. You could hear it slowing down, and there's an encoder pulse on the spindle which will register to the software and say, okay, it's slowing down, don't panic, adjust the pitch accordingly. But the problem is that pulse only comes once every turn, and depending on when it slows down and when that pulse comes, the pitch could get a little bit out momentarily, which puts a bigger cut on, which then exacerbates the situation and causes it to get a little bit out again, and so on. And so by the time it gets to the end of the cut and it can relieve itself and do the return trip and reset itself, there could have been some thread damage, some tool damage, and that means you're on the limit of what it can do. There isn't enough power driving the part, and this is obviously it. So so that sort of size of steel thread, and remember, this is only free cutting mild steel. I want to repeat the test with a really good tungsten carbide insert tool, but I still think that we would get fairly similar results. So really, this RapidTurn, going off this first test, is suitable for light work, for threads in free machining materials, small threads. I wouldn't like to try and cut a large thread in tool steel, in high tensile steel, for example. You'd run into all sorts of problems. And there's a limit to how many passes you can do to limit the depth of cut before you start getting rubbing and chattering. So, you know, this is a really good test to tell you where the boundaries are. So if you look closely at the thread, you can see the first 2/3 is a nice finish, and then the second third is really torn. So I think what happened was that it's cutting along right on the edge of not enough torque, and then the motor started to slow down, and the signal from the encoder on the spindle tried to rectify that by slowing the feed down to match it, but because there's only one pulse per revolution, it didn't manage to sync it perfectly, and so then it started tearing and cutting out of pitch for the rest of the thread. Now what's really interesting is that it was out of pitch. It jumped up to clearance, and where am I? Jumped up to clearance, came back to the start of the thread again, corrected itself to where it should have been, so the pulse has come back in, and it's picked up the thread beautifully and carried on. So that's interesting to see how that works. So you know, even if you do if you do slow the motor down and cause damage to the thread, you haven't lost your position. You've just done a sort of temporary bit of damage, or a partial damage. Alright, well, let's try cutting it in a piece of 16mm mild steel. It's always nerve-wracking, isn't it? Because you feel out of control. I'm used to threading on a manual lathe where I'm in control. I'm not going to say anything too confident and jinx it. So if that spindle slows down, we know from our other tests that things go pear-shaped pretty fast. And the deeper we go, the more likely it is to slow down, am I right? Although the cut is less, it still probably increases. Down to a core diameter of 13.9. Whoa! That didn't sound very good, did it? We're at 13.8 and we have to get to 13.54. So what happened there momentarily was the swath didn't come out cleanly, the load increased on the spindle slowed down, the cut dug in. I don't know. That sequence of events happened very fast. I can carry on, but it's worrying. Doing it again. No, did not like it. Let's stop before we break the tool. If we haven't already. Okay, let's inspect the damage. The tool's okay, it just survived. But have a look at the thread, this is quite revealing. So you can see down this end of the thread here, it was cutting quite well. It was a good finish for about the first 2 or 3 threads, and all was going well. We're about 3/4 of the way down to depth, and then what looks like happened is that maybe the swath curled in the wrong direction and the spindle began to slow down very slightly, and the pulse from the encoder perhaps wasn't in the right place at that moment, and so the feed carried trucking on even though the spindle was slowing down. And when that happens, it takes a deeper cut, and if it's taking a deeper cut, it slows the spindle down more, and so very quickly it can get out of pitch. If you look at the pitch there, you can see it, 2mm pitch, nice clean thread. But when you get down further down, see how it's getting out of pitch, and by the time you're here, you are quite a bit out. Yeah, you can see it there. I hope you can see that on the camera. It's sort of shifted out of pitch, especially there in the middle. And so that's caused it to dig in, and you've got this teary effect that you're inclined to get with mild steel. So that kind of makes me lose confidence in RapidTurn as a thread cutting machine for steel. If you read the manual, it explains how it works. So for each cycle, it waits for the signal pulse from the encoder in the position that you set here, and so that it's synchronized, and it takes the pass along the thread, comes up to clearance, comes back again, comes down to this position, and waits for the next signal pulse again, and away you go. So that works beautifully all the time. The power of the motor is enough to keep the work turning at that correct speed, and it's in sync. But if the power of the motor is not enough, you're coming along to here, then the rotation slows down and you get out of pitch, at least temporarily, until it kind of resets itself as it goes back through to the next cut. So what that means for me is my big chunky Chinese screw cutting lathe, I'll use that to cut big threads with this type of carbide tool, because I've got a really good range of threads that it will cut quite quickly, metric and imperial. 13.9. 13.7. It's taken a bit of power to drive it. 13.7. 13.6. See, this is a good thing to do to compare it. 13.6 and the final cut 13.54. Maybe spring pass, but so just manually machining it. 13.54 just to get a bit of a comparison. Okay, same tool, same steel, same cutting oil. And it's only just about 10 or 15 cuts, so the finish is pretty nice, just manually machined on the old Chinese lathe. So as far as I can see, the problem is with RapidTurn. So that was worth doing, that manual thread cutting comparison, because it really reminded me, you know, when I was cutting it in the manual lathe, you could hear the load going on the drive system, and that's a big powerful lathe that it's taking quite a bit of torque to power through that, and it's only a 16mm mild steel thread. So I really come to realize that, you know, RapidTurn can do threading in plastic or aluminium or maybe very small threads, but I won't be trying to do any large steel threads with it. It's just too big an ask. If it can't keep up with the pitch and it digs in, you get a big meltdown situation. So, you know, we've got to be realistic about what it can do, and I think I've found where the boundaries are for me anyway. Okay, well, let's try screw cutting a bit of 12mm stainless steel. This time I'm going to use cutting oil. This stainless steel is pretty tough stuff. Trying to reduce the chances of it tearing. Of course, there's still a risk of work hardening. I'm not going to make any bold claims this time. I'm pretty nervous, I'm shaking. I just feel really out of control. I think that's what it is. Calm down, Clifford. It's only a tool bit. Adrenaline. God, isn't that crazy? Maybe that's why we like machining. Maybe that's why we like machining. We like the adrenaline high. Goodness me, that was scary. Well, that's a lovely thread. So that was repeating the Tormach example. They've got a YouTube video. Did I manage to film that? Yeah. They've got a YouTube video. I'll just take it out the chuck and get a bit closer for you. Hold on. Okay, that thread looks pretty good. It's just cutting to the specifications set on the conversational, and that's 12mm OD, 1.75 pitch, 9.85 core, so it's just over a millimeter depth of thread, and it seems to be a doable thread for RapidTurn and in stainless steel. Well, it's free cutting stainless steel, very different from other grades of stainless steel. Of course, fasteners and threads are often highly stressed parts, and you often need to make them out of tough steel, out of stainless steel or high tensile steel. So I wanted to know, well, where are the boundaries? What can be achieved? And Tormach have got a video showing a 1/2 inch, by the looks of it, thread being cut in stainless steel. So this is basically the same size, and yeah, it can be done. But I know from my other two tests that that's around about the maximum you can expect. It helps a lot using cutting oil. Let's just back off a bit here. And I'm sure a lot of you know this. If you use cutting oil, it greatly reduces the chances of the metal tearing, and it allows it to cut even more smoothly. It's almost like adding a free cutting agent. But you know, I know from my other two tests that we were on the edge of it not working, and I could almost sense when it was screw cutting there was a few times it was almost starting to hiccup. So I definitely won't, for myself, if I'm working with engineering materials like high tensile steel or stainless steel, I won't go any bigger than 12mm. I just could do without the stress. Alright, well that probably wraps it up. What have I learned from those three tests? Well, clearly don't overload RapidTurn. If you get to the point where you start slowing down the work rotation, it throws the pitch out momentarily and you get a meltdown situation. So that's got to be avoided. Large diameter work puts more stress on it than small diameter work. Free machining steel is a lot easier to cut than non-free machining steel. And if you want to make a fastener out of high tensile steel, like stainless steel or high tensile steel, I probably use a cutting oil, and I probably wouldn't go above 12mm or 1/2 inch diameter. That about wraps it up. It's been very exciting for me, and I know the limitations of RapidTurn. Still really useful machine because it's easy to conversationally program to cut a beautiful thread. I just won't try and cut large diameter threads with it unless I'm working in acetal or brass or maybe aluminium or something that's has much lower cutting loads. So that wraps it up for now. Thanks for watching, guys. Cheers.